Good morning, everyone. Let's go ahead and get settled. Welcome to Elements 101. Got your notebooks ready? Fantastic. I am absolutely thrilled to be your guide for today's explainer because, well, we're going to explore some of the real architectural wonders of the periodic table. I mean, if you've ever stared at that iconic chart on the lab wall and thought, okay, what is the deal with that massive wide block right in the middle? Or, those two mysterious rows just kind of floating all by themselves down at the bottom? Well, today is absolutely your lucky day. We are going to completely demystify the D and F blocks, so let's just dive right in.
Okay, here's our quick syllabus for today's explainer. 1. Welcome to the lecture. 2. The D block, the transition metals. 3. The F block, inner transition metals. And 4, we'll wrap up with some questions for the next class.
All right, Section 1. Welcome to the lecture.
So, our periodic table isn't just some random list of elements, right? It is a highly structured map. Notice that vast middle section? That houses the transition metals. As you move across the rows right there, the electrons are just busy filling up specific subshells. But then, we have the bottom section, the inner transition metals. Now you might be wondering, why on earth are they exiled to the basement like that? Actually, it's pure practicality. Placing them below just keeps the table's overall width manageable, so it actually fits inside your textbooks.
Moving on to Section 2, D block, the transition metals. So, what exactly makes a metal a transition metal? Well, geographically, these elements are found smack in the middle of the table, spanning groups 3 all the way to 12. But the real defining characteristic, the VIP pass that grants them entry into this specific block, is that their very last electron enters a D subshell. That is the absolutely crucial threshold. It's really all about where that final electron finally settles down and finds its home.
Now, let's look at the math. Treat this like I'm writing a giant equation on the chalkboard for you. This right here is the general valence shell electronic configuration for the entire D block. It reads n-1d, 1 to 10, ns, 1 to 2. And this elegantly simply shows us that the D subshell can hold anywhere from 1 up to 10 electrons.
But what's really fascinating is how that underlying invisible math actually translates into physical reality. Because of that specific architecture, D block elements are all metals. They boast incredibly high melting points, and they act as absolutely essential catalysts in huge industrial reactions. But I've got to say, my personal favorite property, and you'll definitely notice this in the lab, is their ability to form just brilliantly colored compounds.
Because the crucial point here is that chemistry isn't just, invisible math. It is intensely visual. Take a look at this quote right from our foundational text. It specifically highlights the, quote, blue of copper sulfate. Seriously, when you see that stunning bright blue liquid sitting in a beaker on your lab bench, you are looking directly at the visual evidence of a D block element, copper in this case, doing exactly what its D subshell architecture dictates. It really is a beautiful thing.
Okay, Section 3, F block, inner transition metals.
Now, let's transition down into the basement of the periodic table. We've got two distinct families living down here. The top row, those are the lanthanides, and they're actively filling up the 4f orbital. Right below them, we have the actinides, and they're busy filling the heavier 5f orbital. So let's take a look at the architectural blueprint for this F block, and I want you to contrast this with the D block we just looked at. Here, the configuration is n-2 f1 to 14, n-1 d 0 to 1, ns2. Notice right there that the F subshell holds up to 14 electrons. So the math is definitely getting deeper here, literally and figuratively.
And because this underlying structure is so much more complex, F-block elements have some pretty extreme personalities. Many of them are quite rare in nature, or they're entirely synthetic, meaning they're created by scientists in labs. Plus, you really have to exercise extreme caution down here. Those actinides we mentioned, the ones filling that 5f orbital, they are all radioactive.
And I think this brilliantly illustrates the fundamental difference between our two main subjects today. Let's just compare them side by side for a second. In the D block architecture, that last critical electron enters an n-1 subshell. It's essentially stepping one level down. But in the F block architecture, that last electron enters a much deeper n-2 subshell. It is diving 2 full levels down into the core of the atom. And that single microscopic difference in depth, that is exactly what separates a structural metal you might use to, say, build a suspension bridge from a highly radioactive synthetic element that you'd have to create in a particle accelerator. Kind of mind-blowing, right?
All right, Section 4. Questions for the next class.
As always, I'm not letting you go without some homework. Here's your first question to ponder. We looked at the math today, but I really want you to think about the why. Why exactly do we use n-1 for the d block and n-2 for the f block when we're writing out their electron configurations? Basically, what actual physical reality of the atom does that mathematical notation represent?
Secondly, I want you to think back to that beautiful blue copper sulfate. We know D-block elements form colored compounds, but what are the actual mechanics behind that? Why do D-block elements create such vibrant colors, and why are they capable of having multiple oxidation states? What exactly is happening with those electrons to produce those real-world results?
And finally, I want you to look back down at the basement of the table. We know the F block contains the lanthanides and the actinides, but beyond the fact that one is filling the 4f orbital and the other is filling the 5f, what are the specific chemical and physical differences between these two series? I want you to really dig into that, and we're going to unpack all of these mysteries together next time. Thank you all so much for joining me for this explainer. Class dismissed.